Okay, let me talk a little bit about null spaces, because I'm getting some feedback that people are having trouble understanding this concept. Well, there's actually several ways to understand null space. Basic definition is the null space of a matrix A is the set of solutions to the linear system with coefficient matrix A and constant vector 0. Now, you should recognize this is that this is a homogeneous system, right? This is the homogeneous system with coefficient matrix A. So let me just write that here. This is homogeneous system. Okay, now, we've also expressed this same idea in terms of matrix vector equations. A vector x is in the null space if the matrix A times the vector x is the 0 vector. I should probably make that in bold because that's a vector. So I'm trying to do that. So I'll just make that bold. All right. In other words, if you can find coefficients x1 through xn such that a1x1 plus a2x2 plus ... plus anxn equals 0, where aj is the jth column of A, then the vector x equals x1 through xn is the null space of A. I can see where this is kind of confusing because you're making a vector out of the coefficients, right? But you can still consider it a vector. Now notice something here. This n is the number of columns. So it's not the length of the column, it's the number of columns. So let me point that out also. So null space vectors are the same size as the number of columns. Now, in this example, for instance, there's 7 columns. A null space vector will be of length 7. It will have 7 entries. Now, what about the column vectors? Column vectors are only 2. Null space and column space are completely different spaces. Column vectors have nothing to do, directly anyway, with null space. There is some kind of relation, but it's not a direct relation. So if you're talking about linear dependence in column vectors, spans of column vectors, and so on, that has nothing to do with null space. So think about these 3 meanings of null space. It's a set of solutions. You can think of it as a set of coefficients, and you can also think of it as a vector whose number of components is the number of columns of A. Okay, so we've really got 2 different spaces, column space and null space. And they both figure into the dynamics of the matrix. And we'll be talking more about these spaces later. All right, now, here's an example of a matrix with 7 columns. And clearly, these column vectors are linearly dependent. I have put this in reduced row echelon form. And you can see that there are several free variable columns. So we do know that the columns of A are linearly dependent. Okay? But that has nothing to do with null space. At this point, I don't know if the null space has linearly dependent or independent vectors at all. So what I need to do is, to find the null space, I need to solve for the coefficients of the homogeneous equation. Right? In fact, this is 2 equations involving 7 variables, and I can write those down here. Now, if you've done this several times, you can shortcut the process. My first equation, I can just read off the entries of the matrix and multiply those by the coefficients and set that equal to 0. But for purposes of solution, we'll isolate the pivot variable and write that in terms of the non-pivot variables. Okay, let's move over so we can see the x7. Okay, sorry, I can just have to zoom in, I guess. Let's just go to 90, probably 95 is enough. All right, now, the second equation up here, similarly, the second row up here similarly gives me an equation, x4 plus 7x5 plus 6x6 plus 5x7 equals 0. Whoops, made a mistake here. That shouldn't be 5x5. Let's fix that. This should be x7. Always can find some things that are better. All right. So we have this equation involving x4, and I want to solve for the pivot variable in terms of the free variables. All right, so my null space solution has 7 individual variables. It's a vector with 7 components. So I want to write the null space solution as a vector or set of vectors. So altogether, I need to specify all 7 components of the null space vector. That's x1 up to x7. Now we have 2 equations here, but we have 7 components. How does that match together? Well, the free variable components are just themselves. So for instance, since x2 is a free variable, I can write x2 equals x2. So you can see I wrote these 2 equations here. The equation for x1 goes here. The equation for x4 goes here. And all the other variables are equal to themselves. Now what I'd like to do is break this out and write it as a linear combination of vectors. And I can do that. I want to pull out the individual coefficients, of which there are 5, x2, x3, x5, x7, and I just pull out the part of this combined vector that corresponds to each one of those coefficients. So, for instance, x2 figures here and here. So if I pull out just those terms involving x2, minus 4x2 in the first component, x2 in the second component, I get minus 4100000 times x2. That gives me all the contributions from variable x2. Similarly with x3, I have a x3 contribution here in the first component, minus 9, and then an x3 component in the third component, which is 1x3. I can pull those out and isolate those as x3 times minus 9101000, and so on. Continuing this process, I can obtain this arbitrary solution of the homogeneous equation as a linear combination of vectors. And these vectors are in fact linearly independent. And the way you can see that is that if you look at the free variable entries, each one of these vectors has only a single 1 in the free variable entries, and the others are all 0. So for instance, this x2 has a 1 in the second place. All the others have a 0 in the second place. So there's no way that you could write this vector here as a linear combination of the others. And you can do that with all the other ones as well. This second vector here has a 1 in the third place. All the others have 0s. There's no way I could write this vector here as a linear combination of the others. Okay? So there's no vector in this set that's a linear combination of the others. And we have a theorem that says that that means that they are linearly independent. So these vectors here, minus 4100000 and so on, are linearly independent vectors that span the null space. So hopefully that brings out a little bit the distinction between null space and column space. If I wanted linearly independent vectors that span the column space, and this is covered in the linear dependence and spans chapter, all I would do is I would take the 2 pivot columns 1, 0, 0, 0, 1, and those span the set of column vectors. That's obviously true. That's the standard basis. Any 2-dimensional vector can be written as a times 1 plus a times 1, 0 plus b times 0, 1. That's just very direct result. So, okay, hopefully that makes things a little bit more clear as far as null space goes.